Good afternoon. I have schermo, condividi. Are you using my screen?
Yes, but it's the folder, Marisa.
Yes.
Maybe you have another screen that you need to share. If you want, you can close the zooming and reopen it again, and sorry, close the screen sharing and open the screen sharing again. Yep, the PowerPoint we can see now.
So I can present now.
Yes, yes. Put it on full screen. Yes.
Dear colleagues, it is a very great pleasure to be who, as GIREP president, can offer the next GIREP medal. I announce the decision of GIREP to offer the GIREP medal for 2020, which was not possible to assign in 2020, to Geshe Pospiech for significant and durable contribution at all levels to the physics education community. Geshe Pospiech is, since from 2004, chair of didactics of physics at Technical University of Dresden. In 1987, she received a degree in mathematics and physics at University of Heidelberg. From 1988 to 1990, she was scientific assistant on stochastic mathematics modeling at the University of Heidelberg in the Sonderforschungsbereich. Fantastic. In 1992, she was Doctor of Research in Mathematics at the University Heidelberg. In 2000, she received the habilitation in physics education at the Johann Wolfgang Goethe University of Frankfurt with the topics of quantum physics and Weltbild, didaktische Überlegungen, eine didaktische first proposal on this topic. She have carried out a lot of proposals in quantum mechanics. In the same year, she received the prize of the Willkommen Foundation for the best postdoctoral thesis in natural science at the University of Frankfurt. From 2002 to 2004, she was teacher for mathematics and physics at Gymnasium teaching assignment and several universities, Heidelberg, Koblenz, and Frankfurt. We have to mention a lot of merit of Geshe also from 2006 to 2021. She is member of the board of the Center of Teacher Education and Research on School and Vocational Education at the Technical University of Dresden. Since from 2006, she's member of the Study Commission, Responsible Expert Commission of the Physics Department for the Teacher Training Program in Physics. From 2008 up to now, of 2012, she was Deputy Equal Opportunity Office of the Faculty of Mathematics and Science of the Technical University of Dresden. From 2008 to 2012 and 2021, she is Dean of Studies of the Center for Research Education and Research on School and Vocational Studies for Teacher Education degree programs. But this is not the main aspect of her wonderful career. Geshe is active in GIREP from the conference of 1998 in Duisburg. She participated in GIREP seminars and GIREP conferences and World Conference on Physics Education from 1998, contributing with her research on mathematics in physics education and on quantum physics for high school level. She founded in 2013 and lead up to now the GTG GIREP thematic group on mathematics in physics education, organizing the GIREP symposium on the topics of mathematics in physics education in 2016 as preparation for the publication of the Springer book on the same topic. She is what we wanted to have by whole GTG, a Springer book on the GTG topic work. She contributed, in addition to GIREP activities as member of the GIREP board from 2017 to the new election in 2019, applied in 2020. GIREP assigned to Geshe Pospiak the 2020 medal for significant and durable contribution at all levels to the physics education community. And I invite all of you to thank her for the work done, and I invite Geshe to present her own contribution to this webinar. Many thanks, Geshe. Many thanks for all your work for us, for the guarantee to give to all of us about your work, your support, and the quality of what we want to reach in each content, and mainly on the topics in which you are expert, which are mathematics in physics and quantum mechanics. I invite all of you to thank and to share with me. Congratulations, Geshe.
Many thanks, Marisa, and to you all for this deep honor. Thousand thanks also for your very kind speech. I'm deeply moved really by receiving the GIREP medal, and I thank the GIREP board for giving me this great honor. And as you perhaps noticed, the GIREP is something like my scientific home, and since my first GIREP conference, I have participated ever since. And I remember my first GIREP seminar where I had at once esteemed for the special character, which we were allowed to see also in this webinar, where I can talk only by video. And I was always fascinated by the overwhelming enthusiasm of Marisa and exerting a strongly motivating force. And therefore I stuck with GIREP since the first meetings. And I'm very happy now that I got awarded for the work I have done for GIREP, and I thank all of the GIREP board who make this association to a well-functioning research community, and thank you a lot.
My pleasure is double because you are also one of my best friends, so I am so happy as never.
Thank you very much.
Okay, I think we now move on to presenting our last keynote speaker, who is also Professor Geshe Pospish. Marisa before me has said almost everything I was going to say here, but I shall give you a short summary of what Geisha has done throughout her professional career. Geisha Pospish is full professor of physics education at the Technische Universität Dresden. She earned her PhD in applied mathematics at the University of Heidelberg and her habilitation in physics education at the University of Frankfurt. In addition, she is a fully trained teacher for mathematics and physics and has taught several years at gymnasium level. Her main research interests concern modern physics in secondary school with a focus on quantum theory from an actual perspective. The second field of research is mathematics in physics education with emphasis on secondary school education. In addition, Geisha studies the pedagogical content knowledge of teachers in this field. She has taken part in European projects, fostering the science interest of students, and also participated in the project entitled Network Particle World in Germany. She is also responsible for the physics education training of teachers at her university in Dresden. I now pass the word on to you, Professor Pospish. The title of the presentation is An Educational Perspective on the Connections Between Physics and Mathematics. The word to you, please. Thank you.
Many thanks for this kind introduction, and I will start by sharing the screen. I hope it will work.
Yes, it is.
Okay, thank you. I'm glad to speak to you even only on video. The aim of my talk is now to give an overview of the state of the art in research on the interplay of physics and mathematics in school physics education. I think it is nice to start with some quotations of physicists and mathematicians because the thinking of experts in this field might be interesting. We have here the citations of Arnold, the mathematician. Mathematics is a part of physics. Physics is an experimental science, a part of natural science. Mathematics is a part of physics where experiments are cheap. Perhaps it's a bit of a provocative statement. And we have another statement, mathematics is a language plus reasoning. It is like a language plus logic. Mathematics is a tool for reasoning, by Richard Feynman. And another quotation, which is perhaps describing the relation between mathematics and physics. One cannot escape the feeling that these mathematical formulas, it is Maxwell's equations, have an independent existence and an intelligence of their own, that they are wiser than we are, wiser even than their discoverers. So we see that there might be a lot behind the relation of mathematics and physics. And there perhaps are different ways to look at the relation of mathematics and physics. And I could say perhaps there are different opinions if physics and mathematics are two separate subjects. Mathematics is part of physics, physics is part of mathematics, or there is an interrelationship between physics and mathematics, or are they inherently connected to each other and cannot be separated. And in order to answer this question, to shed light on these different perspectives on the interrelation of physics and mathematics, I will take first a very brief look at history to see the variety of possible connections. Afterwards, aspects of the interplay will be described, repeatedly looking at it from the school perspective. Which aspects are important for physics education at school? How is the interplay addressed? After that, I will describe some empirical research results and finally give a short outlook. We start with the history. We have, at the beginning of physics in antiquity already, we have several aspects of mathematical elements. There are first the Platonic bodies to serve as a model for the structure of matter. Geometrical elements, therefore, serve as a means for structuring and modeling. And the Pythagoreans used numbers, small numbers, to describe the harmonies of music, which implied that physics processes were described by numbers. In astronomy, both aspects got together, the geometry and the numbers, to describe the relation of space and time, which was necessary to describe the motion of planets. And in the course of the centuries, more and more precise instruments came that required more and more precise descriptions of the natural processes, which induced more and more the use of mathematics. You see here the precise numbers of Joule's experiments. So we can ask, do we need mathematics to do physics? And there we see that there might be physics without mathematics, physics with mathematics. It's perhaps also with a question mark. We have the qualitative descriptions of Aristotelian physics, who describe motion and free fall, and try to develop a theoretical framework. And later on, there were from time to time phases of explorative experimentation, for instance, in the beginning of electrostatics, where no mathematics was inside, but of course it was physics. On the other hand, we could also see that there was a big development of physics in the times of Newton in description and explaining the motion of bodies. And Huygens used the method of infinitesimal geometrical analysis, and he used different representations, the diagram, language of geometry, and algebraic formulations, in order to get a description of collisions. And these algebraic calculations pushed forward the conceptual understanding of these motions. And from the time of Newton and Leibniz on, the development of calculus, later on in the 20th century, the delta function, pushed forward the description of physics by mathematical tools. And there was always a discrepancy of qualitative and quantitative approaches. And this shows in the quotation of Faraday. I was at first almost frightened when I saw such mathematical force made to bear upon the subject, meant are the magnetic field lines, the induction he discovered, and then wondered to see that the subject stood it so well. So we see that there are several aspects in the interplay, in the role of mathematics for physics and physics and for doing physics. And there we have to ask, how do the physicists shape this interplay? First, there is kind of explanation. If you assume that the goal of physics is to explain natural processes, the question arises as to what is meant by an explanation. I won't go deep into this, but before Newton, a physical process was explained using qualitative physical concepts. After Newton, the predictive power of mathematical formulation became so strong that sometimes mathematical calculation was trusted more than physical intuition and hence served as a kind of explanation. From the view of physics education, the self-awareness of physicists and their image of physics as science plays also a role. A qualitative physical explanation regarded as equivalent to mathematics-based explanations. Perhaps we saw in the discussion today that sometimes the mathematics is hidden behind qualitative explanations. So sometimes you don't see the mathematics, but it is there. But is there always a complete, purely qualitative physical explanation? That I think it's open and depends on the context. Another important thing to think about is the structural role of mathematics, where it implies a mode of thinking that allows logical deductions, laws to be derived from principles, analogies to be recognized in similar structures. And therefore, mathematical structures might clarify similar physical mechanisms. For instance, the exponential function is universally used in decay and growth process, not only in radioactivity. And so teaching generic physical mathematical models, such as, for instance, also the integration of force over distance explicitly, could help students to view the related concepts in a wider perspective. Another aspect is the idealization. Perhaps it is sometimes taken too much for granted, but it also should be made explicitly. The idealization, the neglect of physical parameters under certain circumstances. And in order to be able to idealize, to neglect physical parameters, we have to have some numerical evidence that we might do it, that it is possible. So also the idealization requires some estimation of the order of magnitude of some effects we have. And if we go further, we have the simulation of physics processes and numerical calculation. And these can be applied in a way that it's by rote. Sometimes it is said calculation is regarded not so well suited for promoting understanding. But perhaps we can remember to Maxwell, who wrote, "But as we are engaged in the study of natural philosophy, we shall endeavor to put our calculations into such a form that every step may be capable of some physical interpretation, and thus we shall exercise powers far more useful than those of mere calculations, the application of principles and the interpretation of results," which means that also calculation always has some interpretation and some relation to the physics concepts. If we now go on, what does this mean for the educational perspective? There we can have two different points. One is the emotional aspects of mathematization. Gingras wrote of mathematization as unintended consequences. And one of the consequences reflects in the quotation of Faraday, "I was frightened," and coincides very much with impressions and thoughts many people have today. Actors are excluded who do not understand and master the necessary tools, methods, and ways of thinking. And the German physics educator Martin Wagenschein spoke about the initiated, people knowing physics and mathematics who can cope with it, and the intimidated, the school students that ought to learn physics and have the difficulties with the mathematization. And I think some of the discussion we had in our working group were about to not let people be intimidated, but to make physics understandable, perhaps with mathematics in the background, but not as something frightening. And on the other hand, we have some cognitive aspects of mathematization, which were identified by Quay on the basis of theory of science. He identified 4 aspects of mathematics and physics. One is a communication aspect with a dense formula notation, which at the same time helps to reduce cognitive load for learners in the sense that formula are a help for memorizing something, to remember something. And he also mentioned the precision and the objectivity. For me today, the aspect of communication is the most important, because this dense formula notation we have has to be taken into account and has difficulties of its own. And therefore, we now go really to the perspective of mathematics and physics education at school. There we will see some of the aspects I've mentioned now in the general aspect of doing physics as a science, reduced to what of this is important for school, which activities in the school physics might important for this. One thing I think is always there are idealizations, I think often connected to models. It is used to describe physics processes idealization rely on quantitative estimations of the relevance of one or other parameter. And this has to be made clear to the students, and so that the students really know when do they have to take, for instance, friction into account, and when do they may neglect it. The other thing is evaluating experiments. I indicated this with the precise instruments, but if we do experiments, we have very many different mathematical representations. We work with numbers, we put the numbers into tables, we put the tables in a graphs, and we try to derive from the graphs some functions. And these functions describe the dependency of quantities, and this then has to be perhaps derived from some general principle, which also has to be described in a mathematic way. Otherwise, you might not know if the function is a linear function, a quadratic function, or perhaps an exponential function. It's sometimes difficult to decide from the value we have taken in an experiment. So I think experiments are really using quite a lot of mathematics and mathematical strategies. And the other thing is a qualitative versus the quantitative reasoning. We could, some behavior we could predict on a qualitative basis, for instance, the behavior of an ideal gas, if, for instance, the temperature is rising. But in order to give the precise prediction of the extent of the expansion of the gas, we need the algebraic formulation or a graphical representation where we can read off the values or we can calculate the values. So we have seen that physics and mathematics always go together, that qualitative concepts have some explanatory power, but that mathematics can give more precise information about the physics processes. And this we will go to the correspondence between physics and mathematics, perhaps in a bit more detail, where we really see that we have to switch what we expect of the students if they have to switch between the areas, different areas of knowledge and thinking between mathematics and physics. In mathematics, we have the numbers, whereas in physics, we have objects, physical bodies. Mathematics, the basis are the logic with a method with which we go on. And in physics, we have instruments for doing experiments. In mathematics, we have the proofs. In physics, we have the experiments we are doing. And in mathematics, for instance, we have some axioms where we in physics have experience. Of course, from experience, there can also be derived some kind of axioms, such as the second law of thermodynamics. And you have functions and variables, and there perhaps the both areas come closest together. And there we see that we have the physics, and we have in the mathematics, we have different aspects which supplement each other, the algebra, the calculus with differentiation and integration, and the geometry, which are most relevant on the school level. And now this interplay, which I indicated with the red arrow, should be indicate a model, or needs a model to really to describe the transition between the mathematics and the physics, and perhaps to show how they grow together. And there was a model developed by Uden et al. On the interplay between the physics and the mathematics. And this model, there's a physical world. I look at the physical world with physics glasses. The physics glasses and physics models are here. And there I make some simplification and idealization. And then I start to mathematize, to describe the processes with mathematical means. Might be small steps, might be large steps, depends on the mathematical basis, depends on the group of the learners, until I I arrive at a mathematical model. And this mathematical model then has to be treated by purely mathematical means, and we come back and get a result. And this result has to be interpreted again and again. And also during the mathematization, it would be possible to go back to interpret and to go to the mathematization, to go back to interpret until I arrive at this mathematical model. So it's not a one way and back, but it's a kind of back and forth, back and forth. It's a bit simplified here. And if I then have the result and the interpretation, I can validate it in the world. And this red box, I think this is the place where the most students have the most difficulties in learning, understanding, solving problems, and so on. And this we will look at now in more detail. In order to look at it, we have several aspects to distinguish, which are hidden in the model I presented now. It's the syntax and the semantics, and they correlate a bit to the purely mathematics working, the technical working, and the physical mathematical model, which was the red box somehow. The syntax is a list of symbols together with the rules to produce terms. And we have different conventions in mathematics and physics with unthought of difficulties of students. You sometimes are astonished which difficulties the students have, which rules you think are the same in mathematics and physics, but it looks to them differently. This has to be taken into account. And the other additional difficulty is the semantics, given and extracting meaning to the terms, embedding them into a theory. And therefore, we have really also to think about the semantics, that the difficulties students have in mathematics are even enhanced with the additional meanings and concepts they have to learn in physics. And this we can look at from the learning perspective. If we take this syntax semantic, the technical and the structural role into kind of building to see what are learners doing, what are their skills, what are their views, and how does this go to strategies in problem solving, we arrive in a somehow parallel picture. We have the skills, which are technical, meaning that, for instance, handling formula, just rearranging a formula. The communicative skill, what would be kind of talking about formula and verbalizing formula, and the structural skill, which would be applying the formula in a context, recognizing analogies, and so on. So you see that all these skills have to act together, but the individual student could have a focus on the technical skill, on the communicative skill, or on the structural skill, but only the structural would not help without the technical, and the technical does not help without the communicative and the structural. So all these skills belong together. And kind of similar is the attitude. Students could view the mathematics just as a tool, just looking at math as a tool, just finding the correct formula corresponding to the operational strategy. If I have a problem, I just look at, for the right formula, I set in the numbers and I calculate. The other is a translator that the students know translate between mathematics and physics, and perhaps they have kind of mathematical reasoning, or they see the mathematics as giving structure to physics, and in problem solving they have the concepts in mind. And there is indeed, Ataida and Breker found this in a study with students. There is kind of correspondence between the main attitude of the students and the preferred strategies they apply in problem solving. I will come back to this later. First, I would like to show some of the necessary skills on the technical or syntactic level, and on the structural or semantic level and the communicative level we need, for instance, for algebraic expressions. These algebraic expressions are, of course, with formula. I have some calculation rules for the symbols. I have to use the units in a correct way. I have to assign meanings, the relation of the name and the symbol. And here we see the unpacking of a formula, which is well known. And you see with this many descriptions how complex this is, what students have to have in mind if they want really to unpack the meaning of this formula A equals F over M. And this makes the handling of formula, the manipulation of formula with the concepts in mind so very difficult. It's a lot of information hidden there. And the students often are not aware of the epistemological status of the equations, for instance, of this A equals M over A, or if they have the pressure, they do not know, is it a general principle? Is it a definition? For instance, the definition of pressure, P equals F over A, or is it a law for a special case? For instance, if I want to calculate the hydrostatic pressure. Also, this is important for students to know if they want to apply a certain formula, if they want to describe a physics concept with a mathematics tool. A systematic way to unpack formula in physics education was developed by Wiebke Kuske-Janssen, and she has identified several levels, so to say. It does not mean that you have to go from 1 to 6 or from 6 to 1, but there are different levels of abstraction of formula you would apply in your teaching appropriately. But it is good to be clear about the existence of these levels. One is the levels 1 to 3, which are just verbalizing of the formula, which are direct translation of the formula. The formula is here, and here are just direct translations. And the interesting are the levels 4 to 6, where the meaning of the formula is unfolded in specialized language, depending on the context, or erudite language, or everyday language. And of course, you wouldn't come from these to the formula directly, but it's important for making meaning, for the sense making for the formula. And also, you can make meta-reflection about the formula, which is put here. So, so we see that the interplay is quite complex. What I had at the beginning, you see, were very simplified images. Galili has taken this here. You have mathematics and physics and the interplay of these in ever bigger circles, and you have the really intertwining of mathematics and the physics who gets nearer and nearer to mathematics, and the mathematics which gets nearer and nearer to physics, and you have general so-called soft skills of mathematics and physics which you can have. So you see the interplay of mathematics and physics is really very complex, and perhaps you are not even sure, do you use mathematics in physics or not? Because the magnetic field line Faraday has as kind of qualitative physics description, it contains some mathematics. Perhaps the field lines are here, they are not really only qualitative, they are on the way to the quantitative, to the mathematical description. Now I would like to go to some empirical results. What does this always mean? Here I go first to some results on students and then some results of the teachers. It is often said that the students have difficulties in physics because they don't have the math needed. But there has been a study in Germany about the final written exams in Germany. And what came out of this analysis was that the majority of tasks in the physics exam required only knowledge of intermediate level, school level. So it might not be that the mathematical difficulties are the core difficulty. And also mostly technical skills rather than structural reasoning was required. So the difficulties have to lie elsewhere. This is supported by a study about graphs and physics learning, where there, of course, we have the typical errors of graphs the students make, especially if they have to interpret graphs in the connection with kinematics. But a study was done with linear graphs with tasks in physics and mathematics and in other contexts. And the students, the first year students at university, they solved the mathematical task significantly better than the absolutely parallel physics tasks. They were really absolutely parallel. And they even solved the non-physics context also significantly better than the physics tasks, and a bit weaker than the mathematics task. But what is also very interesting is that in the non-physics context, the students applied significantly more creative solution strategies. So in physics, they were somehow constrained by wanting to apply some formula or the other. So this might be a hint of where to look, how to teach students the mathematics and physics, because I find this study quite instructive. The other big role are the algebraic expressions. And when I started work on this, I was astonished how few studies there were on algebraic expressions. One of the first were the symbolic forms, and others were the difficulties students have in working. Shirin has made a big work with the symbolic forms where you have to match somehow the mathematical meaning of all these expressions, somehow the plus, minus, and equal sign, and to match with the physical meaning. You can have a correct mathematical meaning, but if it does not fit the physics problem, then you get difficulties, and this makes it difficult. And one difficult also is that most students tend to work either in a mathematical mode or a physical mode, and so they don't see really the interrelation of both modes, which Uden tried to pinpoint with his model in the red box. Then the students have different strategies in problem solving, and I just want to be very shortly highlight the most important point. The most important point is that students can have surprisingly expert-like strategies. But of course, they need more time to solve a given problem. But not every strategy they have is a novice-like. This has to be taken into account. And I think it fits to the lecture yesterday by Susan Gatt, who said, children are able to more than you think. And also students at school are able to more than you think if you let them do it. And sometimes the students have no balanced view. They refer to the mathematics and they say mathematics is more important than my physics intuition. They don't trust themselves in the physics, but sometimes also the other way around, which was observed when students worked on physical mathematical tasks. And Ataide Greker, as I said, found that the epistemic views on the interplay are related to the problem-solving strategies. Another point concerns the oops, I some is, I see it now. Other thing is the physical mathematical representations. You have different representations, and how do they, and it is said, and I think it's also plausible, that a physics problem you get only in a complete way if you have several representations, each highlighting one aspect of a problem. Here you see the formula table and the diagram which represent the physics law. And the question was, how do the students transfer between one representation and the other? And there we saw that the students had partly quite elaborated views and techniques, and they had as much technical consideration as structural consideration. So even students of 8th grade, 14 to 15-year-old, are able to really structural consideration in transferring from one representation to the other. So the structural role of mathematics and physics can be taught at this age. So what do we do? What are the teachers doing in order to try to convey the technical or the structural role? There is not so much known about what they are really doing, but the general view of teachers, of physics teachers, I just put physics teachers in Google and look for images, and you see that it's all with the formula. And the fuller the blackboard, the better. But that's not really what physics teachers are doing. It's a public image, you see. If we really ask teachers what they are doing, perhaps they are doing something like this. It's not mathematics at all. But you really see that there are quite different and sometimes quite sophisticated epistemic views on the interplay and the teaching principles they are using. And in an interview study with some teachers, I had these so-called types of teachers. I could identify these. The first type of teacher was the concept-related teachers, who like it first to induce an understanding of the concept before I treat it with math. And these highlight more the structural elements of the interplay. Some which are more math related perhaps stress the technical role, but it does not imply that they never mention the structural role or the language aspect of a formula. They just are very much focused on mathematics. And the application related is perhaps the biggest group of teachers. They think of the motivation of students and think if they teach the physics and the mathematics in physics with help of applications where the students see the sense of the applying the mathematics, they get the motivation of students. And there are teachers who really try to cover different aspects depending on the situation and depending on the class they are before. And in conveying the structural and technical role, they really have to use language in order to talk about the formulas. And there we made a study where we really recorded the language of teachers during lessons in 8th grade. And there were 3 big areas the teachers spoke about. One was the formula is just spoken. It's a basic level where the students learn to how do I speak the formula? What can I do with the formula? The second is the formula is spoken about, where the teacher reflect on the formula, on their role for physics and epistemological views. This is here. You see, there are quite a lot of aspects the teachers are saying from the epistemological and from the pedagogical view. And the largest part is the formula is applied or interpreted, focusing on the relationship of variables and so on. And also here you see difference between the teachers. We had about 10 teachers, and you see that some are really speaking a lot about formulas or apply formulas a lot, and some, for instance, here apply it a lot but talk less on the epistemic views on and reflect less on the formula, and some really reflect quite a lot on the formula. And so you see different characteristics of teachers. Because the time has moved on, I want to go to the teachers PCK, which really shows that the teachers have views on the role of mathematics and physics, which inform their teaching principles, which then has influence on their teaching strategies, where they really have different strategies. Some teachers on the technical, some on the structural, but you could not say that one teacher only makes the technical aspects, at least not with the teachers we observed in the students. And also they have some knowledge regarding students. And if we want to be in teacher education, we should make the teachers aware of the complexity of this interplay, and also of the abilities, not only of the difficulties the students have, but also of the abilities we saw in their handling of physical mathematical tasks, which were really challenging for them. If we all have these results, we ask what has to be researched, and I think there's still a lot to do. We have to develop teaching materials and really research the efficacy of materials highlighting the verbalizing of formula, or to develop diagnostic tools in order to really evaluate what do students know about formula and graphs. Shape an explicit didactics of the formula, because it's still missing, and an explicitly didactics of graphs. We know a lot about the interpretation of graphs, but we know far less about the creation of graphs and the reasoning in making graphs. And so we really have a lot of research doing in mathematics and physics education, and we only have done the first step towards all this didactics of formula and didactics of graph. And many thanks for your attention.
Thank you very much, Professor Costa. That was a very interesting talk to highlight this link and interplay between mathematics and physics is something we always think about. But I noticed when you put up the picture of what the public image of physics is, all the formula and all that behind the teacher. Well, the public really believe that physics is mind-boggling and difficult to learn. So maybe that's why the public image was that. But thank you for unpacking these ideas and telling us more about the historical evolution of things. I would like to ask participants present now to ask their questions, if there are any. Any questions, please? You can raise your hands.
Can I break ice?
Yes, please.
First of all, many thanks for so wide and in-depth presentation of this very, very important and big problem. I have some question related to at which age, in your opinion, can we start the meta-reflection you have done on what mathematics role is? Or, according to your experience, when can be obtain profitable awareness by students of the role of mathematics? Because if we never discuss about epistemic aspects or on the meta aspects, we are sure that in-depth analysis were never done. So I ask you to...
Yes. In an interview with a teacher, she said that you have to start early on. If you start only in high school, it's too late. You have to start the mathematics from an early age in order to get the students used to this type of thinking. And when I had interviews with students of grade 8, I was at some point astonished how they thought about formula. So I think you can really start as soon as the students have some cognitive, metacognitive capabilities. And I think you can start perhaps implicitly in one way or the other, quite from the beginning of physics teaching. And perhaps in Saxony, we have kind of advantage, disadvantage. The first formula the students learn is in grade 6. And therefore, there we can start to do it implicitly. I think in a way similar as Susan Gatt did it with very small children, that they applied physics inquiry. We can teach them how to handle a formula, how to speak a formula, how to give meaning to the symbols, not just to memorize the symbols, but give meaning to them. And I think this can start as soon as they learn the first formula. And I think from grade 8, the latest, you can do it explicitly, thinking about the role of mathematics and physics. Of course, in a way appropriate to the age, that's clear. But I think you have to start early so that the students, this is the idea, that the students get used to it, that they have to give the formula a meaning and they do not have to memorize the formula.
Any more questions, please?
There's a question.
We had a question from David Sands. He's allowed to talk, actually.
Yes, of course.
Okay, thank you. Can you hear me?
Yes.
Yes, good. Thank you, Kesha. My question is related to what you just said, actually, but I was approaching it from a slightly different perspective, because I know Joan has done an awful lot of work in mental models, but I've become very, very convinced of their importance, not just for learning physics, but how we reason, in fact. And I came across some work recently that was suggestive that students, certainly in higher education, had mental models of mathematical processes or mathematical mental models, and they had physics mental models. And the students who could apply the mathematics to the physics effectively could actually relate the two different kinds of mental models. And it seems to me that there are certain concepts that we have which imply mathematical relationships. You know, we think of relationships, and proportionality flows, you know, it's embedded in those certain relationships between certain things. And I wondered, to what extent does the mathematics sort of flow naturally from the way that we think and from the mental models? And is there any work on that connection, really detailed work on that connection between mental modeling and reasoning and mathematics?
I don't know quite exactly what you think. What we have in mathematics are the so-called basic ideas, which were developed by from Hofe, and it's mostly German literature, I have to admit, where he really analyzed how basic mathematical operations like addition or multiplication can be understood by students, and how the understanding, for instance, of addition, there are several mental models you can have about how you add or how you multiply. And this has influence on how the students solve problems in mathematics. And I think one of the keys are the symbolic forms, where Shirin really has analyzed that there can be different meanings on the plus sign in physics also. And I think what the students have to bring into congruence, and what perhaps influences their success in physics, or if they find it difficult or not, is how flexible are they in the mathematical basic ideas, and how flexible are they in the physics so-called basic ideas of, for instance, adding as adding two equal parts, or base and change, and so on. And if those are matching, then they will have success. If those are not matching, they have perhaps some kind of error. And I think, but I do not know work about this interrelation about the mathematic basic ideas and the physics basic ideas, and bringing them really strongly and really detailed together.
Okay, thank you. That's very interesting. Could you put a reference to that work in the chat so that I could at least check it?
Which work from Hofe?
Yeah, the one that you mentioned that's in German. My German isn't very good, but I'm sure I can find some translation somewhere.
Okay. Okay. Perhaps I have some English second. Okay.
Well, if you can't find it in the chat, just email me.
I have some. It's even in English. I'm not sure if it's in English. The title is in English, but it's a German journal, so I'm not sure if it's written in.
I'll make some headway.
It's written in English.
Oh, excellent.
If I may say something, generally, I used to find that my students used to think of the formula first, and then were not able to explain the physics concepts. Sometimes, and generally, that used to happen. So I don't know whether you want to comment on that.
Yes, I think it happens quite often, especially if you have numbers in the tasks. And Uden, who did a study, he observed that if the students don't get the numbers at first, they have to be forced to think first about the concepts. If they first get the problem, they have to think about the problem and how to solve it. And if they only after that get the numbers, the probability is higher that they first think about the concepts and try to imagine the situation and what aspects they have to take into account. And then they solve the problem mathematically. And sometimes, and one of his proposals was really to give the students a formula and tell them, please tell a story to this formula, so that they perhaps have to refer to physics concepts because they have to tell a story, and then perhaps one could try something of this in order to make them more flexible.
Yes, in fact, I used to say, tell your story, what you have in your mind. Just say it.
Yes.
Well, thank you very much. I don't think there are any more questions. Yes? No more questions, so we can move on to the next item.
Okay. Thank you very much, Joan. It is now time to share a summary of the ideas that were discussed during the sessions in the work groups. I would like to take the opportunity at this point in time to thank all the work group leaders for their behind-the-scenes work and commitment to such GIREP events. All your contributions are deeply appreciated. In this webinar, we have 3 discussion sessions, and the 6 work group summaries of what was discussed in each work group will now be presented by the work group leaders. The time for each presentation is around 10 minutes. I would like to invite, I think it's Peter, who will be taking over to discuss and present work group 1-2 summary of ideas. Peter, the floor is in your hand.
Yeah, thanks. Yeah, I will open presentation. Yeah, okay. I hope you see my presentation. So work group 1 and 2, we have together this webinar, and it was a very truly international experience, very nice experience. We tried to keep the discussion in 3, me and Lars, Johan and David, and the sort of summary. We discussed technologies physics teachers use in their work, and also how physics teachers support pupils in their use of such technologies. Technologies, we mean both digital technologies and something like standard technologies. It was workshop 1st and 2nd, 1 and 2, and quite nicely was discussed pupil as an expert. If they use, if we use smartphones, the newest type of smartphones, sometimes some pupils are more used to use such technology, such equipment, like a teacher, and it is a very nice open question, but really not open question because it was also in previous type of digital technologies when the pupils had much more time to play with it. And on the other hand, the teacher has some goals and know the physics contents, knows how to use the technology for development of or for physics education. So this is one nice topic. Next we discussed, or then no, next we have discussed this all 3 days, and just there is some attempt to structure the summary of the discussion, how technologies and experience, and even we went to some ground of how experiments are essential part in physics education. We intended to discuss technologies, digital or new technologies, but we often see in many schools that some teachers still use try to teach physics without experiments or without real experiments. Of course, in digital technologies offer also some models or some not real but virtual experiments, but these are also very fruitful. What is very strange for me, but probably not, probably also for me, the limited lab capacities at schools, and that science laboratories sometimes are not built new at schools, but sometimes are disappearing from schools, which sounds very, very strangely. And this is very open topic also to focus on politics for people who are who can decide how to distribute the money focused to education. Yes, what needs to be added or changed to the physics curriculum? This is also a topic because some technology allows go much deeper in some topics, and the time is limited for physics education, or the physics like part of science education is limited. So the digital technologies open also the question about the topics or about just curriculum. Here is a framework from German-speaking countries mainly, which quite help to make a structure to the open topics. Here are some more general competencies or technologies. Here are more specific competencies or technologies, and we didn't use very often these 3 days within our discussion, but we see that this structure can add a new value to our future discussion. The competencies, when we discuss competencies, very often was very sound that the both sides, laboratory and methodology, or equipment and methodology, needs to be taken together. And methodology acquisition versus participatory approach is something which would be nice to discuss more, and mainly in the schools where the participatory approach is not used, because the new technology allow such type of experiments which are planned by pupils itself. Sometimes we say that open inquiry, but experiments planned by teachers, experiments planned by pupils is found to be very important for development of pupils, even from the low age. So this is not only for higher schools, but also for lower secondary schools. Yeah. So such equipment allow also very simple, very simple task to solve. This is one example how to measure the force which was used to prolong something which was put to fly. So the force sensor in the hand of pupils at age of 14 is, I think it already discussed. It is topic to solve. Yes, and very big topic is teacher education. Very nice best practices was presented mainly from Israel, but also Germany and Slovakia. And still we discussed that this is political question, that equipment for physics education is very necessary part of development of physics education, but of course the methodology is also necessary. And question how to test the competencies of teachers is still open, and it was found not trivial solve this, and very different for the preparation of the future teachers and in service teacher training. Yeah. What was quite nice that most of discussed topics seem to be invariant for technology used. for data acquisition and data processing. Even classical voltmeter or spring Newton meter, which we have 50 years, most of the topics was very the same if we use Arduino or smartphones or sensors or classical equipment. And some other have differences, e.g. modeling, computerized modeling is completely, is quite different. So this need special discussion about the methodology. So this is summary from our discussion. Thank.
Okay, thank you very much, Peter, for your concise and precise input. I don't know whether there are any questions that anybody would like to raise at this point. If there aren't any questions, we go on to the next group, which is Work Group 3. Work Group 3, Developing and Evaluating Teacher PCK in Quantum Mechanics, Tools and Approaches. I think Sergey will be presenting this, yes, am I right? Okay, the floor is yours, Sergey.
Yes.
You can start your presentation.
Thank you. Okay, so we were discussing teaching quantum mechanics, teacher education in quantum mechanics. And we started with presentations, and from the presentations emerged that, for example, Jurčić and Paul mentioned that only about 50 to 60% of teachers feel confident to teach quantum mechanics, and this number might even drop once they are in school with the reality of school. De Angelis, Jurčić, and Sutrini mentioned that mentioned the needs that emerge from various questionnaires that they submitted to students, to teachers, and what they would need to effectively teach quantum mechanics. Then Frieriks and Palotta mentioned that there are courses which combine texts, work with videos, and different elements to combine into a course for teacher education. And the most important conceptual ideas to teach would be superposition, entanglement, measurement. We weren't quite sure about the state of the system. This remains a little bit open. Sutrini mentioned that there are simulations that can be easily done in Python, but there are also other tools. For example, HTML5 is also quite fine for doing simulations. Then there was the importance of discussion was pointed out by Sutrini and Didish, that teachers really value the opportunity to discuss between themselves or with experts, be it experts in quantum mechanics or experts in teaching quantum mechanics. Didish then further mentioned that we should teach teachers using active engagement so that they would use active engagement when they teach their classes. Palotta and Chiofalo pointed out that mathematics is very important in quantum mechanics, and that it usually needs to be simplified, and then that there are alternatives to mathematics, which could be graphical visual representations or other symbolic languages that take the role of mathematics, but that some sort of this kind of language is necessary to conceptualize the concepts of quantum mechanics. Staderman and Paul pointed out that we need to pay attention of teaching quantum mechanics, that it shouldn't be just something that students need to learn, but that this need to learn should be given from experience, from devices, from applications, from interesting phenomena and stuff like that. So to foster this need to know, and we need to pay also attention to what teachers need, because teachers already have a lot of experience, and they have a lot of experience in teaching, and so in quantum mechanics they need to we need to take account of this experience they already have. Staderman and Frieriks pointed out that using what I already mentioned, that there are different resources, but that so in one case, these are already organized in a MOOC, and in the other case, these are just given as possibilities for teachers to organize them by themselves. And then Keofalo mentioned that games play an important role in quantum mechanics because in learning quantum mechanics, because they offer the opportunity to experience quantum mechanics, which is almost impossible in any other way. We had some questions to pose to our contributors, our discussants, and two questions were: what types of teaching resources are effective for teacher education and why are they effective? And they mentioned interactive simulations, interactive games that teachers can also develop by themselves, that don't need to be computer games. Laboratory apparatuses. In some countries or in some settings, teachers are not equipped with apparently even basic apparatuses for quantum mechanics. Then teachers often miss from which they could learn either the PCK of quantum mechanics or even the various approaches to quantum mechanics, because most textbooks use historical approach. High school textbooks or university textbooks are rather formal, and some textbooks on different approaches would be valued. Videos of experts explaining the topic, discussion either with peers or with experts or both, questionnaires and tutorials that can be administered to students to gauge their understanding of various concepts of quantum mechanics, and that applications of quantum mechanics can be used as motivation for learning. So how these particular elements, resources act, laboratory experiments can serve as motivation, simulations can focus on various aspects of the experiment more clearly and can serve as a bridge between the experiment and the theory, and games, as I said before, can be used to assimilate the rules. And all these tools need to be integrated into a coherent approach to learning. This learning experience was discussed in the next question, which is what kind of teacher education is effective in some way, or we reduced it to what are the essential elements that must be included in teacher education in order to make it effective. And here we pointed out that already mentioned fostering exchange between colleagues and between experts, then support by experts in different phases in preparation, design, and implementation, in the sense that we shouldn't just tell teachers these are the topics of quantum mechanics, now go and teach them, but we should provide them with for school. When they prepare their lessons and their plans, they should be given support by the experts, either in the course of the preparation, or even if this is a in-service teacher, preparation could also be after the course. And one thing where they could also have some help from experts is in analyzing student understanding. As I mentioned before, tutorials and questionnaires to gauge student learning. Conceptual ideas in focus. We mentioned, and Professor Vokos mentioned in his plenary, that understanding the fundamental concepts is fundamentally important for teachers, and we agree with this in quantum mechanics. The teachers should understand the basic concepts on a conceptual level, and the usual learning done in university levels, where they go through the technicalities of quantum mechanics, might not be enough. The simplified mathematics emerged again. So some tools that can serve as symbols to conceptualize quantum mechanical ideas and concepts. Even games and visualizations can be used for this purpose, like constructing the wave function from some basic forms or something like that. So, and another point that was emphasized was considering affective issues. So how people feel when learning quantum mechanics, in the sense that we must make them make it relevant to them. And in the context of teacher education, we must make it relevant to the teachers also, not just because they have to teach them, but make them listen to them, what they want to know and what they count. So what does a proposal that is usable look like? We need to have applicable and practical learning environments. Again, listen to the teachers, what they think they can do in class, and take them into account when you teach the teachers. Taking into account the learning goals of students and of teachers. Supporting teachers in the design phase and in the implementation phase through micro-teaching, discussions, discussions with experts, tutorials, designing tutorials, and giving meaning to the resources that are available. So giving a coherent path through some resources and the didactical use of these resources, not just showing that resources exist, but also how to use them in a didactically relevant way. And at least one approach should be gone through with teachers so that they see what an approach looks like from the beginning to the end. But we specified that it is very important that they have even different perspectives on the same topic. So see also different perspectives. Now, for the points in the position paper that we want to produce, I will repeat some of the same stuff. We have teaching supports of different kind, laboratory simulations, games, what I already discussed. It is relevant to integrate them into a proposal. Teachers have to experience this integration, go through a particular resource and see how it works. A teaching proposal has to be offered to teachers in a teaching course. It is relevant to discuss with teachers the main concepts of quantum mechanics and how they are different in and how the different concepts are viewed from different perspectives. Different approaches view them in different perspectives, and this is important to discuss. Even if we only show one approach in the entirety, we need to discuss the other perspectives on the same concept. Okay, learning goals are always a priority. The fundamental concepts to be discussed are I already mentioned. Then we have teachers often don't have time for planning, so we should help them there. And as I said, we could have some already prepared short courses. Metacognition as a result of reflection is highly relevant. So teachers need to discuss and be confident in what they learned and ask if they are not sure, so that they can also be flexible in what they produce. Affective aspects I already mentioned, and in this already technology which can lead to motivation, mathematics and different strategies in different contexts. Just a few more. These were the points that emerged after the discussion today. We need to take into account different backgrounds and different learning goals, which can vary significantly between countries and between schools. School system and exams are also important constraints. We already mentioned this, assessing the learning outcomes. Yes, of course. So assessing the learning outcomes is important for students. And one point that was made very important was that physics is an experimental science, and experiments should be carefully included into the teaching of quantum mechanics, chosen which experiments and what is their didactical value in the view of the goals that we want to achieve. Thank you very much. This was all from my part. Thank you.
Thank you very much, Sergey, for the detailed summary of the outcomes of your work group. Maybe we can now go on to work group 4, in-service physics teacher education for early childhood and primary levels. I think it is Dagmara who's going to present. Okay, the floor is yours, Dagmara.
Thank you very much. I will share the screen with you. Do you see it?
Yes.
Okay, good. All right. So the title of work group 4 was in-service physics teacher education for early childhood and primary school, and I will speak on behalf of the entire group, but in particular on behalf of 3 leaders, Mojca Cepic, Marco Giliberti, and myself. Here is our group at the very beginning, just gathering for the first oral session, oral presentation sessions. Each session included 6 presentations only. The group was not big, but the discussions were very fruitful. So WG4 issues already indicated in the description of the work group provided before the conference are indicated here. We indicated 6 issues, and for the discussion, participants from 5 countries gathered. Usually we had like 12 to 13 participants in each session. So first, yesterday we addressed physics education and pre-service teacher education. So we wanted to learn at which age physics topics are introduced in each country. Also, what age is spent by primary education, and also at what age physics starts as a separate subject. So in most countries, primary education covers 6 to 11 years old students. Physics topics are introduced in most of the countries already in the kindergarten, except Poland. Teacher education for that kind of introduction only of just topics and issues is not very demanding. In Spain and Czech Republic, it's just a degree in teacher education, but in Poland, Italy, and Slovenia, master degree is needed for kindergarten and also for the primary education. Physics as a separate subject starts at age 12 to 14, quite common in all countries, and the educational demands to teach physics are master degrees in physics or physics education. In Italy, you can start as a master in maths and then get some more training. Also in other countries, if you have a master degree in mathematics, chemistry, something similar to physics, you may get another training to become a teacher for 2 subjects. Okay, in-service teacher education in particular countries, here we had more variety. In most countries, however, there are no obligatory demands for CPD. So in Slovenia, in Poland, however, a motivational system of promotion exists. The promotion means usually to get higher salary. So Slovenia has 3 levels, Poland 4 levels. For all that, not obligatory, but still existing CPD in each country, government systems do not offer much. Rather like the second subject courses I mentioned before, or few regional trainings. On the other hand, CPD is offered by other institutions like handbook publishers, private companies, NGOs, mobility in Erasmus Plus, by those institutions who can offer that. Several universities take initiative for CPD, and a fantastic example of informal network of physics teachers having regular meetings exists in Czech Republic, and it's called Elixir to Schools. So we proposed some solutions. So we think that CPD should be obligatory at least once, maybe in 5 years, maybe in 3 years. More systemic solutions supported by government, changing attitude towards physics, So more global initiatives should be taken, and practical CPD for teachers. So the CPD should not be, as it usually is, organized like a theoretical, again, a lot of work lectures, but rather like labs and workshops. So more of systemic initiatives are needed. Universities should take the leading role in in-service CPD. Teachers need us and appreciate collaboration with us. CPD should address teachers' need and be very practical. Here is the topic we did not discuss this year, but because it was elaborated at large scale last time. So formal, non-formal, and informal aspects of physics education at primary level and relations between them. Last year, we came to the conclusion that all three styles of learning should intertwine, because each style benefits the other two. And non-formal and formal learning should be much more emphasized and promoted in pre-service teacher education and in-service teacher education. And also competitions are important for increasing motivation of students. The second session this year was sacrificed to learning formats and tools. So we learned that in all countries, we come from qualitative knowledge to formulas. And in general, the development of formalization is gradual. So students usually start with drawings, histograms, of course, text, tasks, then simple math, expressions, and then graphs. Lab activities are not developed enough, in our opinion. Games are more frequently used. Outdoor activities are more common in the preschool context. Science days, again, a very nice idea from Slovenia. They organize science days, obligatory science days at all ages, starting from primary. And storytelling enriched with experiments. This is something that is proposed in Czech Republic. I will come back to that in a minute. Inquiry-based learning, this is what we found. Inquiry-based learning is not very common right now, still not very common after 14 years of promoting it. But there are projects in each country to foster its use. When teachers learn how to do IBL through practice, not theoretically, because it doesn't work, but through practice, and apply IBL in their classes, then they start to really love it, and they stop to be afraid of that. So the conclusions are: context, students' own experience should be a starting point in learning any topics in physics. We should use more the active learning strategies and instruments in order to support learning of physics more and more and more. Use of storytelling enriched by simple experiments. This is the proposal from Czech Republic, checked by them. So storytelling with simple experiments can encourage teachers to do experiments. There are some teachers who do not do experiments, but if it is embedded into a storytelling, then they can do it. The use of a mathematical representations and ability to switch between them should be emphasized. Probably Geshe would be happy. Much more practical CPD in IBL on a larger scale is really, really needed. Okay. About textbooks and ICT and other tools. So textbooks are mostly used for exercises in some countries like Italy and Poland. They are used like a Bible. In Czech Republic, primary teacher use also YouTube, videos, textbooks, workshops in science centers. So more or less textbooks plus some other tools are used, not very frequently. ICT, the use of technologies is increasing. This is good news. Videos, animations, and applets are used. Some physics textbooks have virtual components or online content. However, the strategies for using textbooks should be taught during methodology courses. It looks like this is not a topic of the pre-service education, but it should be. ICT cannot replace, we agreed upon that, they cannot replace hands-on experiments. However, it can be very supportive. and applets open opportunities to schools that have no labs, and in many countries, especially in the villages, small towns, etc., there are many such schools. We should promote an active use of technologies, not only to watch videos or share presentations. It is not enough. Activity is very important. How about topics suitable for early ages? All topics in physics, in fact, but of course, adjusted to the age level. So floating, surface tension, diffusion, friction, basic properties of air and water, other matter, simple heat experiments, magnifying glasses, mirrors, shadows, electricity, optics, magnets, you see, everything except quantum mechanics, maybe even quantum mechanics, as it was emphasized in the first keynote. How diffuse and how strong is the link between universities and physics education research groups? So actually it depends on the country. For instance, in Czech Republic, the link is very strong, even if not all universities that do pre-service teacher training use the physics education research outcomes. In Italy and Poland and also Spain, I forgot to mention, not too many links between universities and primary schools. So the conclusions are: physics education research units at the universities play a crucial role in organizing CPD and its internationalization. So physics education research units should be more active in transferring current results of physics education research to teachers, and improvement of collaboration between universities and teachers is crucial and urgent. The last session was organized today, so we focused on the question: which approaches to teaching and learning early science are most common in preschool and in primary school. In preschool, mostly observations and playing. In elementary, some activities, but more on observational level. Indicated problems: active work is suggested, but we do not know how much it is implemented. Poland finds no physics topics, unfortunately, at early ages, which is really backthrow. Spain teachers often follow textbooks quite strictly. Which approaches are usually included, discussed, introduced in pre-service and in-service trainings for teachers of early science? In Poland, nothing. All countries emphasize experimental work and its methodology in teaching and learning. In service trainings, when they are offered, focus on new experiments accompanied by various methodological approaches, which is very good. Then the last topic was about tools and resources helping teachers teach physics in kindergarten and primary school. So which tools teachers use in addition to oral explanation? For example, ICT, games, simple experiments. Again, it was repeated demonstration, small projects. How often students meet those tools? Teachers are inventive. They use experiments, projects, movies, quite a variety of them. But they very often use textbooks only. Again, we come again to this format of using textbooks. The opinion of Czech teachers is that one experiment per week is good, but they use the same experiment several times. And in other countries, it is like maybe a few times in a month or something. And the last question: which resources teachers usually use for preparations of early science lectures? For example, peers information, textbooks, etc. Resources vary from following textbooks to web and popular books with experiments. Early science teachers are often afraid of questions. However, in Czech, physics wrapped in stories helps to reduce this fear. Okay, and I would like to thank all WG4 contributors for their fantastic work and fun we had. Thank you very much.
Thank you, Dagmara. There are 2 questions in the chat, Dagmara, for work group 4.
Okay.
Can you take a look at them and address them, please?
Okay. Yeah, wait. Why motion? First one probably up.
Could you explain?
The WG4, could you explain a bit more on storytelling connected with experiments? I cannot, because it's not my idea. Okay, so it's an idea from Czech Republic, from Jitka. So they have a source. It's unfortunately in Czech language. However, if Itka is still with us, or Mojca has this link, probably she has, we can put it maybe in the chat. So the text is in Czech, but the storytelling was based on very common international fairy tales. However, Czechs added to those fairy tales some experiments. Okay, I have already something. Okay, how it works. So it works this way, that normally teachers are afraid of doing experiments, but when they have the story to tell, so they start with the story, it's much more natural. That's what the Itka says. It's much more natural so for them to do an experiment as a stop. So they stop at some moment, do experiment, small experiment, simple experiment with children, and continue with the story. Why does it insensitive to carrying out experiments? So probably I already explained that. Why motion, where the Galilean principle of relativity and forces are not suggested to work in primary school? Okay, 6 to 11. Motion, of course, but relativity, ooh, not really. Okay, that's it. I believe that Eilish has another.
That's something else.
Yeah, something
Thank you
else.
very much.
I hope I answered. If not, please refer to Itka, but I believe nobody, Itka is not here anymore. I will try to search for the link for those who are interested. Oh, Itka, could you put the same, Itka is here, the same link you provided to us for storytelling in Czech language with experiments? Thank you so much. Okay. Right.
Okay. All right. Thank you very, very much for your
Charles,
detailed
there's a
summary.
question from the audience as well.
All right.
Can I allow?
Where is it?
A raised hand.
All right. Yes.
Okay.
Yes, you can ask the question, please.
Okay, I come back, answer the question. Yes, but I cannot see who. So
Neither I.
yeah. Can we have this question? The person speaking?
It was Moika. She said I can put it if Jinka allows. I think she it's referring to the link.
Okay.
Okay.
So I'm done. Okay,
All right.
thank you very much.
Thank you very much for your presentation. It is now the time for work group 5 leaders to present their summary. I think it's Susanna, is it, to present?
Yes, hello
right.
everybody. Hello everybody. Just a second, I will share my screen with you. Can you see it?
Not yet.
Not yet, okay.
Yes, okay.
Is it okay? Okay.
It's
okay. So hello again. The working group 5 dealt with the issues of pre-service physics teacher education at all levels. There were quite a lot of authors of presentations, and the group was led by Claudio Fazio and myself. We had 34 co-authors of 9 contributions. And this is the list of the contribution. The participants were from Italy and Spain, so we had majority of Italian participants, and most of the contributions were dealing with primary education and various issues concerning physics, pre-service physics teacher education. We proposed several topics for discussion, and we continued we built on the last year Malta discussion, solving or discussing the issue of developing competencies of pre-service teachers to effectively enhance physics teaching and learning in active learning environment. So this is still in the focus of people involved in education, because we still think this is an issue that is not completely solved, and there are many open questions in this field. Concerning pre-service teachers education, we were discussing that there is a different attitude to primary teachers education and secondary teachers educations, since primary teachers education is involving more psychology and pedagogy from the first years of the study, while secondary teachers education is mainly content oriented in the first years. Usually the bachelor part concern content oriented subjects, and in the following 2 years there are psychological, pedagogical, and physical education courses. So from this point of view, these primary teachers, they get in touch with various methods of active learning, maybe at earlier stage as the secondary teachers do. And these teachers, they only start about talking methods of teaching at the last 2 years of their study usually. The other thing that we were strongly stressed, and everybody was approving this idea that if we want teachers to teach in this way, they have to experience active learning strategies by themselves while they are learning. So we think that these strategies should be involved in education of pre-service teacher education, even in content-oriented courses. These content-oriented courses, as the participants said, are usually based on transmissive ways of teaching and learning, lecture plus calculus plus labs, and very rarely they involve active learning elements. Even the lab work that complements these subject-oriented courses is built as cookbook experimentation with very little space for inquiry. Many participants were reflecting on this issue, that the lab work itself, it's not inquiry-based lab work usually. We mentioned various possibilities how to implement active learning approaches even in lectures. It's already known that there can be interactive methods implemented in even in large-scale lecture rooms where we have many students. We can even though present, for instance, experiments in a very interactive way, as proposed by David Sokolov and Thornton, who developed this procedure of realizing interactive lecture demonstrations. So we think that general courses or introductory courses should involve at least this kind of active learning elements during lectures, if not in the other lessons that pre-service teachers participate at. Another option that was mentioned by the participants is that these general courses, for instance, like mechanics or electricity, etc., these basic courses that each pre-service teacher education student is involved in, could implement projects that can be assigned to students. And this project can involve a problem concerning the topic of the course. So for instance, a kind of problem from mechanics that can be solved in groups by students during the whole semester when they work on it independently. And even though this is a subject-oriented course without any didactics at this level, they can start feeling what this active learning approach, inquiry approach means, because they can experience it by themselves while working this way. This project seems to be a good option to enhance active learning at this stage. After the bachelor, usually the countries have courses on education where the attention is paid to methods of teaching physics. So in these courses, these various methods are analyzed in detail. So this in countries, they have such courses where students, pre-service teachers, for instance, play a role of a student, and they experience what is expected from the student of secondary school, for instance, or primary school. So these methods are then in detail analyzed during the special courses aimed at didactics of physics or physics education courses that are in the last 2 years, as far as for the participants that participated in our discussions. In this field, in some countries, a lot of work was done within various projects that supported this kind of approaches. For instance, in Slovakia, we were running a large national project aimed at in-service teacher education, and a lot of work has been done. A lot of lessons have been developed in order to support this kind of teaching and learning approach. And these materials that were developed, they are also used at university level. So they are provided to all people who work in the field of education, and they can be implemented in secondary education, or also for pre-service teacher education. So this is what we can summarize from the question concerning active learning environment. So we strongly emphasize that teachers should experience this way of teaching while studying at the university. So not only these didactic courses, but also other courses should involve some elements of active learning. The other question that we were dealing with is the question of online teaching that we are facing for almost 2 years, and since 2020 we got more experience in this field, and I think teachers as well as teachers, educators find their ways how to support online teaching. This question is how to prepare teachers for online teaching, and what activities should be involved in pre-service teacher education in order to prepare them for online teaching. Because even though this pandemic situation will be over, I think that many of these technologies or methods that we develop in order to support online teaching can be helpful for us in the future. So we divided these problems into 2 parts. One part is mastering digital technology that we consider maybe less difficult. That means digital technology to support online teaching, like learning management systems, Moodle, Google Classroom, etc., and other various technology that supports creating online quizzes, surveys, voting, like Poll Everywhere or Kahoot or Google Forms. Some countries, they have special courses on on the use of digital technologies for teachers. So in these courses, they are acquainted with various technologies for supporting teaching and learning. More important question we consider experimentation, since physics is based on experiment, and once we are in online space, then this way of experimentation cannot be conducted. So there are various possibilities how to conduct experiments even in online space. This is not hands-on, so it does not bring benefits of hands-on experimentation. That is very, very important. However, as a good compromise, there are several possibilities that pre-service teachers should be acquainted with, and they are acquainted during their own studies. I suppose that as far as for our group, participants were commented that while we were provided this online teaching, we were also running laboratory works, etc., etc. So we had to replace many real experiments with some other tools that could help us to get what we wanted from lab work and experimentation. So we mentioned several useful things to support experimentation. Very good option is to use remote control experiments, and there are various web pages and schools that provide these remote control experiments when we can connect and collect data, and we can see also the video of the experiment and collect data. So this is a good option to replace real experimentation. Another thing that we were commented is that real-time measurement with sensors, for instance, can be recorded together with the video recording, with the experiment. And these two things, like video recording and measurement, can be replayed at the same time. So you can watch the experiment in the video, but at the same time as the experiment is running, you are watching how the data are collected. So this is really beneficial, and students can collect data on this while they are watching the experiment itself. So this is not virtual but real, recorded on the video. So this is also a good option. Then we were talking about video measurement that also enables to collect real data from video recording of real situation, motions of different objects that can support mechanics a good way. Then, of course, virtual experiment simulations can be used. Also, it was mentioned that YouTube experiments can serve as good motivation for experimentations to start to discuss about the topic, for instance. Then we are talking a little bit about augmented reality, and the video game tool was mentioned that was quite new for me, Microsoft Kinect or Kinect, I don't know. That is a device that can that was designed for a game, and you can use it for measuring position. It's much more sophisticated as a position sensor that we have as a part of real-time measurements. So this is a summary of what we discussed concerning online teaching. And the last part, we were dealing with preparing non-physicists to be physics teachers. Is that even possible? This was a question that we tried to answer. And this question arises from the fact that in many countries there is a decrease in number of physics teachers, and physics teachers are needed a lot, and new physics teachers are not graduated or are graduated in low numbers in many countries. There are various reasons why this is occurring. In each country, it may be a little bit different. These reasons are different. So the question is, can we prepare other teachers to become a physics teacher, for instance, or how can we help in this field? And there are different routes in various countries. For instance, in Italy, only mathematicians, engineers, and physicists can be involved in teaching physics. If they want to become a teachers, they have to participate in pedagogy and psychology courses to gain certain number of credits, and then they can teach. No other teachers are allowed to study to become a physics teachers, or no other subjects oriented people. Just mathematicians, engineers, and physicists can enrich their education into physics education. In Spain, there was some remark about physics and chemistry that can be taught together. And in Slovakia, the way how it works is that in-service teachers from schools who have a different specialization can enroll into university for a 2.5 years course. When they come to university for 1 day each week, and in 2.5 years they can get or can be graduated. They do not get a diploma, they get just a certificate that they can teach physics above their own subjects that they were graduated. So there are many problems with this kind of education, because not only mathematics teachers can apply for this course. So if there is a teacher who is not a mathematician, or he, for instance, teaches geography and English language, he has got a lot of problems in mathematics still, since mathematics is a language of physics and we need it a great deal. So we suffer with a lot of problems in this field. We have only 3 countries participating in the discussions, and the number of participants were quite low last days. Last day we were just a few. So this is all that we could produce in these 3 days, and I would like to thank to all participants and to my colleague Claudio for fruitful discussion. Even though we were just in a small number, it was a nice experience for all of us. Thank you.
Thank you, Susanna. And I don't know whether there are any questions that you would like to ask. Maybe if not, we can go on to the last work group 6, in service physics teacher professional learning for second and higher level education. This presentation will be made by the 3 work group leaders. So it's Eilish, Wim, and Gerald. It's up to you. Thank you.
Okay, our slides are controlled by, whoops, Eilish. Uh-oh.
Eilish hasn't control, it seems.
She says she's not listed as a panelist.
She's not listed as a panelist. So we'll have to take care of that.
No, she is on the panel.
Yeah, her name is showing.
I do not have access as a panelist. I don't know. And Anthony, she said it in her chat.
Ah, because there were 2 Eilish. Now the real Eilish will be on the panelist.
Okay.
Ah.
Hello, fantastic. Brilliant. Now I have control as a panelist. Thank you. Can you see my slides?
Yes.
Yes.
And hopefully you can see the careful color coding we have going on in work group 6. And the reason for that is I'm going to introduce, and then as we go through our working group, we focused on second and higher level education. Wim's comments are going to relate to second level, therefore he's red. And Jerry is going to talk about higher level, and therefore he's blue. I hope that's all clear to everybody. So workgroup 6, in advance and on the website for the webinar, we posted out 6 questions relating to second level and to higher level education, numbered A to F under each heading. We are going to go through each of those sub questions around the discussions that happened in workgroup 6 over the last 3 days. What we did was we had the presentations from the 9 contributors on the first day and partially the second day. And then after that, we asked each of the presenters and contributors to contribute to each of the 12 questions, 6 at each level. Then we asked each participant to make a contribution of the summaries of each question. And then today we spent time going through all those contributions and making the summaries. So I hope I have explained that this was really a group effort, and what Wim and Jerry would present was the contributions of the whole group. On the right-hand side there, you can see a nice example of the feedback questions on 1D question and the summary at the end. Okay, so I'm going to control the slides, and then Wim and Jerry are going to tag team this as we go through.
Okay, there we go for the first question on the second level. What strategies are used for physics teachers' professional learning? Out came several traditional ways of strategies, namely workshops and courses made available online by all kinds of partners, organizations. Also, outcomes of projects are made available, and all these people, they hope that teachers will look at them and adapt them in their own teaching, and in this way learn more about their own profession. There are other newer strategies, for example, collaboration between teacher group with a university facilitator, so in which the group decides to develop new ways of teaching, either content or pedagogy, test them in the class, and then come together again in a group and to see and to exchange experiences and to improve the course on that topic. So that was a new strategy, more in depth, takes longer, but has better results, I think. Another idea is support for novice teachers, which we heard about learning assistants, in which these teachers are explained better their role, their learning path, and then subsequently are supported by an experienced teacher in going through that learning path in real live class teaching. Of course, some countries oblige teachers to attend learning activities. You can consider that also as a strategy. And then last but not least, maybe the concept of professional learning communities is also been introduced. They get different names. For example, DPLC in Israel or COPE in Malta, or also in the DRIDIFI project, we used this concept in which we really on a regular basis bring teachers together on a certain issue, certain questions, and make them exchange their experiences and their expertise.
Okay, thank you, Wim. So I appreciate that this year we introduced higher level education as one of these threads in this working group. This is a different question here for question A, which is what's the requirement for educators for teaching at this level? And the answer is essentially none. I'm not trying to be that funny. There aren't formal requirements for the teaching, unlike the secondary teachers who have to get licensure or certification. There's no such formal certification for university instructors. Basically, you get hired as a faculty on the basis of, let's say, your research experience. You have a PhD, for example, to be a university professor, but your training admittedly is mostly in your disciplinary field, your research. And you don't have particular pedagogical training leading up to that point generally. So there are no certificates of pedagogical training that are needed. There are possibilities for instructors at university level to develop their own pedagogical talents as grad students or postdocs. or as early faculty who have recently been hired, but none of these are required or mandatory. And in fact, many instructors don't even know about these opportunities. And so we'll talk more about that as we go. But they're available, and they're often very high quality, but they may not be accessed by many instructors. And again, I emphasize it's optional. And most of these things are offered by the institutions themselves through centers of teaching and learning, or centers of teaching excellence, or something like that. But there are no formal qualifications.
Okay. Question 2 then. We
Okay.
have
The second question, what opportunities for continuous professional learning are available? So on the level of the school, this district, region, country, and I would even say internationally. One new idea is in a certain country where they establish structural contacts between university experts and teachers. So they create channels for exchange of expertise there as a support for the teachers, which is a good idea. Of course, teacher education organizations, universities, they always offer courses and workshops about learning or information activities. Some countries, they provide deep learning by the teachers via an intensive course, more like an education to upgrade their diploma, and it's often supported by government. We also consider that as an important element of teacher learning projects. So Erasmus Plus project partners in Europe offer courses as outcomes of projects. Communities of professional educators, teachers teaching the same subject, they meet together on regular basis, and then they discuss their practices about certain topics maybe, and including pedagogical innovations and exchange experience. And also other opportunities could be that teacher professional organizations, every country probably has one, IOP, AAPT are examples. They offer discipline-specific workshops or thematic workshops, courses, and conferences, which are also opportunities for teachers to learn.
Okay, and as you can see, this question is very parallel, and I think from now on, most of the questions for secondary and university level will be parallel. So I'd already mentioned the opportunities offered by institutions through their centers of teaching and learning. These again are advertised and open to people to attend these events, but again, they're not required. The second bullet is more or less similar. You can have development events, and you can have things that focus on scholarship of teaching and learning. Let me maybe jump to bullet 4, which is professional societies do offer some opportunities for these occasions. For example, at least my experience is many of you, I hope, have been to AAPT meetings. And before every meeting, there is a series of workshops, many of them, 30 or 40 of them offered on many different topics. And a lot of them are about pedagogical development. So those are opportunities offered twice a year at the specific meetings through AAPT. The third bullet is particular doctoral and master's courses. These probably are more for, if they're in education, more for secondary teachers who need certification or licensure. But of course, university folks people headed for university teaching can obtain these degrees and have them as part of their development. Again, most of the university people will have specific physics degrees in a research area, nuclear physics, atomic physics, solid state physics, whatever. And then aside from the offers by institutions or societies, there exist more and more online resources that anyone can go to at any time of the day or night and engage themselves in self-learning and self-help. And I'll say a bit more about that later.
Okay, the third question was the easiest one to answer. Continuous professional learning, is it about content pedagogy or both, but in most cases, both content pedagogy get enough attention. There is one rather new or one rather specific element, I think, on the second level, is that when government introduces new curricula, for example, then a lot of these continuous professional learning opportunities, courses, etc., are in view of the novelties or innovations in the new curriculum.
So the answer to this parallel question for the higher level is different. Content is generally not emphasized because if you have been hired, presumably, let's say with a PhD to university faculty, you are nominally an expert in your field and the foundations of physics. So it is expected that you know the content very well. And the part that's focused on in the professional development is therefore the pedagogy. I don't want to try to say that university instructors come in with no knowledge of pedagogy or no experience. Their experience generally has been that they themselves have been taught as students, and maybe they have been teaching assistants as grad students, but that doesn't really cut it when it comes to really handling a class. So all of the things we worry about, pedagogical methodologies, is largely lacking in these folks, and that's where the emphasis is. As one of our members had pointed out, instructors, I think, know very well, what they know, they're experts, but they don't really know what the students know or what the students think or what the students' ideas or misconceptions are. So that is something they need to gain awareness and some training in. And so I would say for the university folks, higher level, the focus is mostly on pedagogy.
Okay, the fourth question is what online resources are available to support teacher professional learning? As you have heard from the previous contributors to these summaries, a lot of online resources, of course, are available. The only problem is to make them reachable to the teachers. Teachers lose their way in all these links and all these online materials and lack the skills to distinguish good from less good, etc. There are a few examples like UNAM, FISTEC, Scientix, FET, you know them all. They are all, some of them are used a lot and also implemented, especially now during a lot of online lessons, that online libraries, journals, etc., are also used to improve their teaching. Also, I think Susanna already numbered a few online applications, and we also got two examples like Plickers and Desmos that facilitate the teaching and learning a lot in these times where computer is so important.
So again, the parallel question for university side, the AAPT has sponsored this development of the FISPort website. I would actually urge any of you that do not know about FISPort that when this meeting is over, you Google FISPort and take a look at it. It's been developed over several years, and it's a phenomenal collection of all kinds of resources. I would like to emphasize one important point. When I say resources, I don't mean only teaching resources like good lesson ideas or interesting experiments for the advanced lab. What I mean is specific resources also for professional development. There are videos of teaching assistants and learning assistants in action with real students. And these are used to guide classroom discussions for teachers of what techniques are good, what did the TA do that was good or bad, and analyzing the actions of the teaching assistant or the instructor. There are, again, videos which are active, not passive. So FISPort has a lot of stuff It's been very highly developed, sponsored by AAPT. Advance HE, I gather, is from the UK. I'm sorry, I'm not from the UK, so I'm not sure what's in it. That may be sponsored or directed by IOP, Institute of Physics. And then you could probably find other sites out there from other universities for helping to train their own faculty that are open publicly, accessible, and you could tap in and see what they have to say about professional development.
Okay, so the next is over 2 slides, and it's about the barriers and incentives to pedagogical innovations at second and higher level.
Yes, for teachers, innovation is a problem in the sense that they're most of the time a little bit reluctant to change. This is not only because they are conservative, but they have a lot of other elements they have to pay attention to. There are a lot of trends and issues the schools bring forward, the government brings forward, and they have to take them all into account. But in general, this ends up in a certain reluctance to change. Also, time management is a problem because from experience and from trying out, they have to conclude that many of these innovations are very nice, but time consuming. And so they get a little bit stressed as that they will not be able to reach the curriculum goals at the end of the school year. Another difficulty in all these pedagogical innovations for many teachers is to assess the learning of the students. They might be convinced that students indeed are improving their learning or they're getting better results, but these results, to assess them, to turn them into points and percentages, because that is in many cases still so important, it's difficult for them to learn how to assess these new and innovative teaching methods. Another, rather practical issue is teachers don't feel they get enough salary, and maybe this reduces their motivation for attending all kinds of professional development sessions. On the other hand, they know, and there are many examples of that when they succeed in improving the learning and motivating the students, then everything goes more smoothly. For one of the examples is giving positive feedback, and also giving them to the students, but also asking the students for feedback. And in general, at least my experience as a teacher coach, in general, students are really, let's say, engaged and have a positive attitude towards the learning of the teacher. This can also engage students and enhance students' engagement in the whole learning process, which is always in a combination with the teaching process. And if both do their best, teachers and students, this for sure will lead to better results. Another nice incentive, very importantly, last year's, is that collaboration between teachers, and not necessarily of the same discipline, but of course, it helps when they are of the same discipline. They can work together on resources and all kinds of aspects about their practice to use during the lessons. And sharing these resources, of course, spreads the good news, spreads the improvements that are at stake.
So the barriers and incentives topics are pretty similar for the university case. Time management, which includes not only preparing the innovative curriculum or pedagogy that you want to deliver, but also how much time it costs in the classroom and the obligation to cover material. In particular, I think universities have much larger classes often than high schools and secondary. So that's a particular challenge for innovative pedagogy. Essentially, you have resistance from multiple sources. You can start at the top, and the administration can not support your efforts either philosophically or financially. Okay. If I jump to number 7, your faculty can resist that. Again, they can believe because of the way they were taught in lecture and they just absorbed it all, that the regular conventional method, it's always worked. Why change it? Worked for them. Why doesn't it work for the students? What many faculty don't realize is the students in their classrooms are not wired the same way that they, the university faculty, are wired. And then you can have pushback number 6 from, number 5 from the students. Often the innovative pedagogies require more effort and work with the students, getting them to struggle in real time. And they want to just sit and listen to the lecture and maybe look at their email. So you have these possible complaints from different constituencies. Also, how will you assess that your method has done better? If you try it, you have to be able to prove it's working. That's challenging. And the other issue related to students is, especially in universities, we have end of semester evaluations in all courses. And sometimes the students that struggle and you challenge them, they complain. And for newer instructors seeking tenure, negative feedback can be detrimental. So that's a fear factor for some people to institute innovations. However, and having done it myself, the rewards are well worthwhile. You can see how you can improve the learning of the students. We apply scale-up collaborative group learning at our school, George Washington University. The group work and collaborative environment is tremendously beneficial. It's much more fun for the instructor and the students. It's more dynamic. It's not passive in any way. And students like it better. Once they realize that they're working and having some degree of fun and learning, they are actually more satisfied in the end. Sometimes universities will offer faculty awards for innovative and excellent teaching, and you may get recognized in that manner also.
Okay, so our last question was in relation to the impact and how do we evaluate the impact of these measures? And I suppose one of the things that was highlighted was there's a difference between measuring the teacher professional learning and evaluating teachers for promotion purposes. And we strongly believe of the value of evaluating teachers' professional learning. So at the second level, we saw examples and heard from the contributors of teacher questionnaires and surveys and interviews being used. Again, like Jerry said, the student surveys at the end of the year, some classroom observations. The findings that the authors reported were around the feedback from the teacher was collected, but actually not the impact on the teachers or the students. They're not really widely measured. And certainly the question on whether there's an influence then on the teacher professional development is very open. Some examples of the awareness of teachers' awareness of pedagogical content and knowledge modules and self-efficacy, and on student learning gains or student development. We also focused a little bit on the purpose and the use of the evaluations. They can be for who is assessment for? Is it for the teacher, for the student, or for the authorities, and how that might be used? So we were looking for examples and we saw very little of use of evaluations on the teacher's development of knowledge, skills, etc. And I just have on the right-hand side the example there from the Neutron Stars project, which did actually contain examples of all of these different types of assessments they used in this project. Sorry, the last question was on a higher level then. Again, really high dependence on these student surveys end of year, some measures on the learning gains of the students. I suppose the caveat is that the end of year student surveys had no link or didn't appear to have any influence on the teaching quality or the professional learning of the faculty. And again, we'll highlight some of the examples from our contributors from the Institute of Physics. It's good to see that the new criteria for physics accreditation of degree programs focuses on teachers being able to apply their knowledge and skills rather than focusing on their content. The example of the Rethink Seminars Network, they use these videos of dialogues between professors and a researcher to discuss scientific articles focused on educational research. And the Scale Up project had examples of student learning gains assessed by national diagnostic instruments. So again, some good examples of that. But this 3 days work has been very interesting and enjoyable. And we would be remiss unless we thanked all of the contributors from work group 6 that are named here on this slide. And we thank you for your attention.
Okay, thank you very much. All were group leaders, and I don't know whether there are any questions before we conclude. Okay, so I'd like to once again thank all our group leaders, and the GIREP 2021 webinar is coming to a close, and now I would like to invite Marisa and Joan to give the concluding messages for this webinar. Marisa and Joan, the floor is yours.
Here I am.
And also me, I shall say a few words before I introduce you, Marisa. Well, I hope that all the participants have enjoyed this webinar. Hope you will all take something with you, some ideas from the keynote speeches and also from the discussions that you have had in the different work groups. We all hope that these meetings help us to become better teachers of physics. And we also hope that they help us to help others perform better in their teaching roles. From our end at the University of Malta, it was a double effort, in fact, but also a double satisfaction to have cooperated with GIREP and also the GIREP board members for having these webinars, these 2 webinars in 2020 and 2021 being run in this way. I would like to say something also about paper submissions to all those people who have submitted their abstract. We obviously invite you to submit your papers. There will be a deadline, which will be the 15th of February 2022 for submissions. Later on, we will put this information, all information required, on the website, on the GIREP Malta Webinar 2021 website. And please follow the guidelines for the paper layout, because obviously that will help us to finalize the work even in a shorter time. Finally, now I ask the GIREP President, Professor Marisa Michelini, to deliver her concluding note. Thank you. Marisa.
Thank you so much, Joan. Welcome to the closing ceremony to everybody. We as GIREP decided to invest in the quality and the value of in-depth discussion in the second challenge of the remote meeting. We focus on the ambiguous goal of selected contribution on 5 main topics, in each of which high-level responsibles coordinated in an in-depth discussion on relevant questions chosen to produce position papers. Very excellent plenary talks were offered on the same topics by the keynote speakers, Professor Andrea Schwerb, Federico Corni, Susan Gatt, Stamatis Vokos, and Geshe Pospiek. It was a great pleasure to meet, even if at a distance, so many colleagues from many countries. I have here, and I thank the local organizing committee, the list of participants: Brazil, Canada, Colombia, Czech Republic, Germany, Hungary, Iran, Ireland, Israel, Italy, Malta, Netherlands, Nigeria, Poland, Slovenia, Spain, Turkey, Uruguay, UK, US. Already the first result now presented here in the last session tell us that we were right. I was reached by comment of satisfaction by many working group participants and from the same tired responsibles, the results presentation evidenced the richness of the work done. We have now to write the papers of the accepted contribution and to send additional contribution integrating the discussion held in the position paper written by responsibles. So please don't avoid to send additional contribution if during the discussion you were inspired for that. We will produce a selected paper book with Springer and selected paper IUP proceedings open access. These will be a very great opportunities for us because we are working with a special agreement offering us free of charge the opportunity to diffuse our work and to have indexed publication in such a prestigious editorial systems. You will receive guidelines soon by editorial group of IUP proceedings and selected paper Springer book. Let me thank one more the Malta Local Committee, Charles Bonello, Anthony Galea and Joan Bormarks, assuming the responsibility to organize the webinar, working so hard and producing a perfect environment for our fruitful work. Let me thank GIREP board and in particular Dagmara Suklowska, Vice President of GIREP, and Elish McLaughlin, General Secretary of GIREP. Let me thank the responsible of working groups. They are working a lot in this before the webinar, in this period, and have to work additionally for the position paper. Last but not least, many thanks to all of you participants for offering your work and contributions to the discussion of the webinar topics. A new initiative is announced now. A new initiative of GIREP is announced now. Thanking the support of the family, we decide to promote a prize which name is Sara Barbieri Award, proposed by Marco Ciliberti from Italy, 1,000 euro offered by Sara Barbieri family each year for a research carried out by a teacher or innovation carried out by a teacher. An international commission will select the contribution that we hope will be a lot. In GIREP website, in a week, you will find the conditions to take part to the award. And I ask you to spread as much as possible the information that we will offer, starting from Ljubljana, the first Sara Barbieri Award. Why Ljubljana? Yes, I invite you to continue to work on the discussed questions in the next Hanoi third WCPE is now open. The call of contributions, it will be held in December. So we are very close, and please be so kind to support, which will be the first World Conference on Physics Education online. Many countries will participate, thanking to the work on Wim Peters and Paul Logman, taking the majority load for this organization. I invite you also in Ljubljana for GIREP conference next July. The announcement of such events are already on the website. You will find the detail and the possibility to ask questions and to contribute by means of suggestions. So look at www.girep.org as where you can find everything which is useful. Let me thank you one more for participating. I hope you are satisfied for these 3 afternoon of works, very dense, but I find it very rich, and I hope it is the same for you. Many thanks.
Thank you, Marisa. Thank you, everybody.
Thank you.
Thanks. Have
Thank you
a
very
good
much.
weekend.
Thank you.
Bye bye.
Bye.
Bye-bye.